Every day, billions of people wake up to a world increasingly shaped by forces they cannot see. Algorithms curate the news we read, the products we buy, the people we meet. Machines translate languages in real time, diagnose diseases, write poetry, and drive cars. This transformation happened gradually, then suddenly. Artificial intelligence, once confined to science fiction and research laboratories, has become the invisible architecture of modern life. But how did we get here? And where, exactly, are we going? The ambition to create thinking machines is not new. In 1950, British mathematician Alan Turing published a landmark paper asking a simple question: can machines think? Turing proposed a test, later known as the Turing test, in which a machine would be considered intelligent if a human evaluator could not distinguish its responses from those of a person. The question was provocative, even radical. It suggested that thought itself might be computable, that the human mind might operate according to rules a machine could follow. 6 years later, in the summer of 1956, a small group of researchers gathered at Dartmouth College for a workshop that would change the course of technology. John McCarthy, Marvin Minsky, Claude Shannon, and others proposed a research program they called Artificial Intelligence. Their ambition was bold: to simulate every aspect of human learning and intelligence using machines. They believed that significant progress could be made in a single summer. That optimism, though premature, launched a new scientific discipline. The first wave of AI research produced impressive demonstrations. Programs like Logic Theorist proved mathematical theorems. ELIZA, developed at MIT in the 1960s, simulated a psychotherapist's conversation. Yet these systems were brittle. They operated in narrow domains, using hand-coded rules. They had no understanding, only pattern matching. By the 1970s, the limitations became clear. Funding dried up. The field entered what researchers later called the first AI winter, a period of disillusionment and stalled progress that would last more than a decade. AI resurged in the 1980s with expert systems, programs designed to mimic the decision-making of human specialists. Companies invested heavily. Mycin, developed at Stanford, diagnosed bacterial infections. Xeon configured computer systems for Digital Equipment Corporation, reportedly saving the company millions annually. But expert systems had a fundamental weakness: they required laborious manual encoding of knowledge. Every rule had to be written by hand. As problems grew complex, the systems became unwieldy. By the late 1980s, another winter arrived. Meanwhile, a parallel approach was quietly gaining ground. Instead of encoding knowledge by hand, some researchers focused on machine learning, teaching computers to learn patterns from data. The idea had roots in work by Frank Rosenblatt in the 1950s, who built the perceptron, a simple neural network. But neural networks required vast amounts of data and computing power. For decades, neither was available. The approach remained on the margins, pursued by a small community of believers while the mainstream focused elsewhere. By the late 1990s and early 2000s, the landscape began to shift. The internet exploded, generating unprecedented volumes of data, text, images, clicks, interactions. At the same time, computing power grew exponentially, following Moore's law. Graphics processing units, originally built for video games, proved remarkably effective at the parallel computations required for neural networks. Suddenly, the ingredients for machine learning were abundant. Researchers who had labored in obscurity found their methods newly viable. The field began to accelerate. In 2012, a team led by Geoffrey Hinton at the University of Toronto entered a prestigious image recognition competition called ImageNet. Their deep learning system, a neural network with many layers, trained on millions of labeled images, crushed the competition. The error rate dropped by more than 40% compared to the previous year's winner. The results stunned the AI community. Deep learning, once dismissed as impractical, had delivered a decisive empirical victory. Companies took notice. Investment poured in. The modern AI era had begun. Deep learning systems learn by example, adjusting millions or billions of internal parameters to minimize errors. A network shown millions of cat photos learns to recognize cats not through programmed rules, but by discovering statistical patterns in pixel values. Layer by layer, the network builds representations. Early layers detect edges, middle layers recognize shapes, deeper layers identify objects. The process mirrors, however crudely, how neuroscientists believe the human visual cortex operates. It is learning, but learning of a profoundly alien kind. Within a few years, deep learning permeated consumer technology. Smartphone cameras use AI to enhance photos in real time, adjusting exposure and focus faster than any human could. Voice assistants like Siri and Alexa rely on deep learning to transcribe speech and interpret commands. Recommendation algorithms on Netflix, Spotify, and YouTube predict what we want to watch or hear next, often with uncanny accuracy. These systems are not intelligent in a human sense, but they are undeniably effective. They have reshaped daily life. One of the most dramatic advances came in language. For decades, machines struggled with natural language understanding context, nuance, ambiguity. Then, in 2017, researchers at Google introduced the Transformer, a new neural network architecture. Transformers excelled at processing sequences, learning relationships between words across long passages of text. Models like BERT and GPT, trained on vast corpora of internet text, achieved near-human performance on many language tasks. Translation improved dramatically. Summarization became practical. The door to conversational AI had opened. OpenAI, a research lab founded in 2015, pushed language models to new scale. GPT-3, released in 2020, had 175 billion parameters and was trained on hundreds of billions of words. It could write essays, answer questions, compose poetry, even generate computer code. Then, in November 2022, OpenAI released ChatGPT, a conversational interface built on GPT 3.5. The response was explosive. Within a week, ChatGPT had over 1 million users. Within 2 months, over 100 million. No consumer technology had ever grown so fast. Generative AI did not stop at text. In 2022, systems like DALL-E, Midjourney, and Stable Diffusion enabled anyone to create images from text descriptions. Artists, designers, and hobbyists typed prompts, "a futuristic city at sunset in the style of Monet," and received original images seconds later. Some hailed it as a democratization of creativity. Others warned it could displace illustrators and photographers. The tools were powerful, accessible, and unsettling. They raised questions about authorship, originality, and the nature of creativity itself. Generative models learn by studying millions of examples, images paired with captions, or sentences followed by completions. They do not memorize, they extract statistical patterns. A text-to-image model learns that sunset correlates with warm colors, that cat correlates with fur and whiskers, that Monet correlates with impressionistic brushstrokes. During generation, the model samples from these learned distributions, producing novel combinations. The output is new, but built from fragments of the training data. It is creation, but of a distinctly algorithmic kind. The impact on work is already visible. AI assistants help programmers write code, drafting functions, and suggesting fixes. Lawyers use AI to review contracts and identify relevant case law. Marketers deploy AI to generate ad copy and analyze campaign performance. Customer service increasingly relies on chatbots that handle routine inquiries. A 2023 study by researchers at MIT and OpenAI found that access to generative AI increased productivity by 14% for customer support agents, with the largest gains among less experienced workers. But productivity gains raise uncomfortable questions. If AI can do more work with fewer people, what happens to those displaced? Historically, automation has eliminated some jobs while creating others, often requiring different skills. Economists debate whether AI will follow that pattern or whether this time is different. A widely cited 2013 Oxford study estimated that 47% of U.S. jobs were at high risk of automation. More recent analyses suggest the reality is more nuanced. AI typically automates tasks, not entire occupations, reshaping roles rather than eliminating them outright. The workforce is adapting, unevenly. Demand for skills that complement AI, critical thinking, creativity, emotional intelligence, is rising. Routine cognitive work, like data entry or basic analysis, is increasingly automated. Education systems struggle to keep pace. Some companies invest heavily in retraining, others do not. The transition is creating winners and losers. A 2022 report by the World Economic Forum estimated that by 2025, automation could displace 85 million jobs globally, but also create 97 million new roles. The net is positive, but the distribution is not guaranteed to be fair. Healthcare offers a glimpse of AI's potential. Deep learning systems now match or exceed human radiologists at detecting certain cancers in medical images. Google's DeepMind developed AlphaFold, an AI that predicts protein structures with remarkable accuracy, a breakthrough that could accelerate drug discovery. AI helps identify patients at risk of sepsis, suggests personalized treatment plans, and even assists in surgery. These applications promise to extend and improve lives. Yet they also raise questions about liability, bias, and the doctor-patient relationship. AI systems learn from data, and data reflects the world, including its inequalities. In 2018, Amazon scrapped an AI recruiting tool after discovering it penalized resumes containing the word women's, because the system had been trained on historical hiring data skewed toward male candidates. Facial recognition systems have been shown to perform worse on darker-skinned faces, leading to wrongful arrests. Algorithms used in criminal justice, lending, and hiring can perpetuate or amplify existing biases. The problem is well documented but difficult to solve. Researchers and ethicists are working to mitigate bias. Techniques like fairness-aware machine learning aim to detect and correct disparities in outcomes. Some propose more diverse training datasets. Others call for greater transparency, requiring companies to disclose how their systems make decisions. Regulation is emerging. The European Union's AI Act, proposed in 2021, classifies AI systems by risk and imposes strict requirements on high-risk applications. But bias is not purely a technical problem. It is social, political, and deeply entrenched. Technology alone cannot solve it. Generative AI has also weaponized misinformation. A deeper question haunts the field: do these systems understand anything? ChatGPT can answer questions and write essays, but researchers debate whether it grasps meaning or simply predicts patterns. In 2022, a Google engineer claimed that Lambda, the company's chatbot, was sentient, a claim widely dismissed by AI experts. The models are black boxes, their inner workings are opaque even to their creators. They exhibit behaviors that seem intelligent, but the substrate is statistical correlation, not comprehension. The gap between performance and understanding remains vast and philosophically troubling. Some researchers believe that understanding may emerge from scale. The scaling hypothesis holds that as models grow larger, more parameters, more data, more compute, they will develop new capabilities, including reasoning and common sense. Empirical evidence partly supports this. GPT-4, released in 2023, showed significant improvements over GPT-3 on complex tasks like legal reasoning and scientific problem-solving. But critics argue that scale alone is insufficient, that current architectures lack mechanisms for genuine abstraction or causal reasoning. The debate is unresolved. Scale has delivered surprises before. Scaling has consequences. Training large AI models consumes staggering amounts of energy. A 2019 study estimated that training a single large language model could emit as much carbon as 5 cars over their lifetimes. Data centers that power AI systems draw electricity on a vast scale, often from non-renewable sources. As AI becomes ubiquitous, its environmental footprint grows. Some companies are investing in renewable energy and more efficient hardware. Others face criticism for prioritizing capability over sustainability. The tension between AI's promise and its ecological cost is becoming harder to ignore. Military applications of AI raise existential concerns. Autonomous drones can identify and track targets without human intervention. AI systems analyze satellite imagery to detect troop movements, predict adversary behavior, and optimize logistics. The US, China, and Russia are all investing heavily in military AI. In 2021, the United Nations held discussions on lethal autonomous weapons, machines that could select and engage targets without human oversight. No international treaty has been signed. The prospect of AI-driven warfare, where decisions unfold at machine speed, is both strategically attractive and morally alarming. The most profound worry is alignment, ensuring that advanced AI systems pursue goals compatible with human values. Stuart Russell, a leading AI researcher, has argued that the current paradigm of AI systems optimizing specified objectives is fundamentally flawed. An AI instructed to maximize paperclip production might, if sufficiently advanced, convert all available resources into paperclips, including humans. This paperclip maximizer thought experiment illustrates a broader risk: systems that are competent but misaligned. Solving alignment is one of the central challenges of AI safety research. Some researchers warn of a more distant but catastrophic risk: superintelligence, an AI system vastly smarter than humans in all domains. Nick Bostrom, a philosopher at Oxford, has argued that such a system could pose an existential threat if not carefully controlled. Others, like Yann LeCun, chief AI scientist at Meta, dismiss these fears as speculative and premature. The debate is polarized. Some prioritize near-term risks like bias and job displacement. Others focus on long-term scenarios involving loss of human control. Both camps agree on one point: the stakes are high. Governing AI is complicated by its global, decentralized nature. Breakthroughs happen in universities, startups, and tech giants across continents. No single government can regulate the technology unilaterally. International cooperation is rare. The US and China compete for AI supremacy, each wary of ceding advantage. The European Union has taken a more regulatory approach, but enforcement is uncertain. Some propose an international body akin to the International Atomic Energy Agency. Others doubt that powerful nations would submit to oversight. The question of who controls AI and on whose terms remains unresolved. In many ways, AI reflects humanity back at itself. It inherits our biases because it learns from our data. It threatens jobs because we organize society around labor. It raises ethical dilemmas because we have not agreed on shared values. The technology is powerful, but it is not autonomous. It is shaped by choices: what to build, how to deploy it, who benefits, who decides. These are human questions. AI does not answer them. It amplifies them, making visible tensions that were always present but easier to ignore. AI is already reshaping education. Intelligent tutoring systems adapt to individual students, identifying gaps in knowledge and personalizing instruction. Tools like Khan Academy's Khanmigo use large language models to provide on-demand help with homework and essay writing. Some educators worry that students will offload thinking to machines, atrophying critical skills. Others see potential for democratizing access to high-quality tutoring. Early studies show promise: AI tutors can improve learning outcomes, especially for students who lack access to human support. But the pedagogy is still experimental. The long-term effects are unknown. AI is breaking down language barriers. Real-time translation apps allow people who speak different languages to converse almost seamlessly. Google Translate, once clunky, now uses neural machine translation and achieves near-human quality for many language pairs. Microsoft and Meta are developing universal speech translators. The implications are profound. Cross-cultural collaboration, global commerce, and access to knowledge could all become easier. But translation is never neutral. Subtle meanings, cultural context, and nuance can be lost. The question is not whether AI can translate, but whether it can preserve what matters. Science is accelerating with AI's help. AlphaFold's protein predictions are enabling new drug designs. AI systems analyze astronomical data, identifying exoplanets and gravitational wave signals faster than humans. In materials science, machine learning predicts properties of compounds, shortening the discovery cycle. DeepMind's AlphaFold has already contributed to research on malaria and antibiotic resistance. But AI is a tool, not a scientist. It finds patterns, it does not formulate theories or design experiments. The creative leap, the hypothesis, the insight still comes from human minds. For now, artists and musicians are experimenting with AI as a collaborator. Composers use AI to generate melodies, then refine and arrange them. Visual artists feed sketches into generative models, which propose variations and extensions. Some see this as a new medium, akin to photography or synthesizers, a tool that expands creative possibility. Others worry about dilution. If AI can generate infinite variations, does anyone matter? The debate echoes earlier anxieties about mechanical reproduction. The question is not whether AI can create, but what creation means when machines participate. AI's appetite for data threatens privacy. To function, AI systems require vast datasets, often harvested from users without explicit consent. Facial recognition allows mass surveillance, tracking individuals across cities. In China, AI-powered systems monitor citizens, assigning social credit scores based on behavior. Even in democracies, data brokers compile detailed profiles, sold to advertisers and sometimes governments. Privacy laws like Europe's GDPR attempt to impose limits, but enforcement is patchy. The trade-off between AI's benefits and the erosion of privacy is stark and increasingly urgent. Could AI ever become conscious? The question is ancient but newly pressing. Consciousness, subjective experience, the feeling of what it's like to be, is poorly understood even in humans. Some philosophers argue that consciousness requires biological substrates, others believe it could emerge in any sufficiently complex system. AI researchers are divided. Most agree that current systems are not conscious, they process information but do not experience it. Yet as AI grows more sophisticated, the question becomes harder to dismiss. If we cannot define consciousness, how will we recognize it in a machine? The frontier is shifting toward multimodal AI systems that integrate text, images, audio, and video. GPT-4 can analyze images and describe them. Google's Gemini processes video and audio alongside text. The goal is a more general intelligence, capable of reasoning across modalities as humans do. Early results are promising but imperfect. These systems still make errors, confabulate, and lack common sense. Yet the trajectory is clear: AI is becoming more versatile, more integrated, and harder to ignore. The tools we use daily are growing more powerful, month by month. Not all AI is controlled by corporations. Open source models like Meta's Llama and Stability AI's Stable Diffusion have been released to the public, enabling researchers and hobbyists to experiment, modify, and deploy AI without corporate gatekeepers. Advocates argue this democratizes access and accelerates innovation. Critics warn that open-source AI can be misused for generating deepfakes, malware, or disinformation without accountability. The tension between openness and safety is fierce. Some call for restricting access to the most powerful models, others see that as a dangerous concentration of power. Regulation is emerging, slowly. In 2023, the European Union advanced the AI Act, categorizing AI systems by risk and imposing transparency and accountability requirements on high-risk applications. The US has taken a lighter touch, favoring industry self-regulation and sector-specific rules. China has issued guidelines emphasizing state control and ideological alignment. The divergence reflects deeper political divides. Europe prioritizes rights and precaution, the US innovation and competition, China's sovereignty and stability. No global consensus exists. The regulatory landscape is fragmented, and AI does not respect borders. Amid the technical complexity, a simple truth persists: AI is a human creation. Every algorithm reflects choices: what data to use, what objective to optimize, what risks to accept. The engineers, executives, and policymakers who build and deploy these systems are people, with biases, incentives, and blind spots. The technology is not inevitable. Alternative paths exist. We could prioritize transparency over proprietary advantage, fairness over efficiency, sustainability over scale. The question is not what AI will do to us, but what we will do with AI. The future is not written. It is being written now. We stand at a threshold. Artificial intelligence, once a distant dream, is now woven into the fabric of daily life. It diagnoses diseases, writes poetry, drives cars, and makes decisions that affect billions. The pace of change is disorienting. The implications are profound. AI will reshape work, creativity, communication, and perhaps consciousness itself. But it will not do so on its own. Every transformation is the result of human choices, investments, regulations, values. The rise of AI is not a natural phenomenon. It is a story we are telling, together, about who we are and who we want to become. The questions facing us are urgent. How do we ensure that AI benefits everyone, not just the powerful? How do we protect privacy, dignity, and autonomy in an age of surveillance? How do we govern a technology that evolves faster than laws can be written? And how do we preserve what makes us human: curiosity, empathy, creativity, in a world where machines can simulate all three? There are no easy answers. But the act of asking, rigorously and honestly, is itself essential. The rise of artificial intelligence is not a problem to be solved. It is a mirror, reflecting our deepest hopes and fears, forcing us to decide what kind of future we want to build.